What I'm going to do is I finished in the middle of something yesterday. I'm going to do a brief recap and then start from where I was yesterday. So I talked about 3 key problems in reinforcement learning, 2 of which distinguish reinforcement learning from supervised and unsupervised learning, and those are exploration, exploitation, and the delayed reward problem. And of course, the generalization problem that's common to all machine learning. And as I said to you, I won't be talking very much about a generalization problem. So we started with bandits. And in bandits, it's purely exploration, exploitation, right? There was no delayed reward problem. We talked about 2 types of problems, planning and learning problems. Planning is where you are given the model of the world to begin with. In bandits, if you have the planning setting, it's very simple. Just pick the arm with the greatest expectation. So it's too simple a problem to spend any more time on. We talked about the learning setting, where you don't know the distributions over rewards, which is the more interesting setting and faces the exploration exploitation problem. We talked about 3 algorithms, right? 3 styles of algorithms. One was the epsilon greedy algorithm, which takes the greedy action with probability 1 minus epsilon, random action with probability epsilon, and it does pretty well. If you want it to converge in the limit to the optimal action, you have to decrease epsilon over time. You can't decrease it too fast, otherwise it wouldn't explore enough. You don't want to decrease it too slow, so 1 over t like things work. Right? So we talked about that. We talked about an algorithm which had sort of a 2-phase algorithm, right? One was the first phase where you explore every arm a certain number of times. And then after you explore every arm a certain number of times, then you pick the greedy arm at that point, and you get a pack style result, right? So you get a pack, a delta epsilon pack style result, where you can show that with probability at least 1 minus delta, the arm you select will be no worse than epsilon optimal. We did that algorithm. We talked about a really interesting algorithm called UCB1, which was the optimism under uncertainty algorithm. There, we figured out what reward bonus to add to the empirical mean of every arm, so that every arm was with very high probability was optimistic in its evaluation. And so there was this very clever idea, or in some ways simple, in some ways clever, idea of maintaining optimistic estimates and then acting greedily with respect to those optimistic estimates. And as your estimates improve, as long as you still maintain optimism, you are going to explore enough and in the limit be purely exploitative, right? So the UCB had that property. So that's what we did for bandits. And then we moved on to MDPs, where I talked about 2 problems, policy evaluation and optimal control. I finished policy evaluation and I was in the middle of optimal control, which is what I'll do today. So what do we do for policy evaluation? Again, there were 2 settings, the planning setting and the learning setting. The planning setting is where you have a model. So planning setting. By the way, the planning setting does not face the exploration exploitation problem, because you're computing in a machine before you actually face experiments, before you do things in the real world. But it does face the exploration exploitation problem. We talked about a small MDP setting. Having a model means you know the transition probabilities, and you know the reward functions, you know gamma, and you were then the policy evaluation problem and the optimal control problems had specific systems of equations you had to solve for the optimal value function or the policy's evaluation function, right? So we did those algorithms, and then we switched to learning. In learning, you don't have the transition probabilities in the reward function. Instead, you get to act in the world. So you're in some state S sub t. If you're doing policy evaluation, well, then you take the action pi of S sub t. You get a reward R sub t, and you get to state t plus 1. And we did TD0, TD lambda, the eligibility traces algorithm for talking about how to learn to evaluate a fixed policy. And then where we were was optimal control, where you don't have a policy. Instead, you're trying to find an optimal policy. And so you take some action AT in state S sub t and get reward in next state, right? And I talked about Q-learning, which is a algorithm on the slide, on the screen up there. And so we've just taken action A sub t in state S sub t, seen reward R sub t, and the next state is S sub t plus 1, right? And now, let's see, where is this? And I showed that just like for TD, if you learn state action values, so there's one clever trick, right? We had to move from state values to state action values because that swapped the max and the expectation. It brought the max inside the expectation. And in doing so, we were able to get an unbiased estimate of exactly the update you would do if you had a model. Notice this is not an unbiased estimate of the optimal value function. It is an unbiased estimate of this quantity, which was this is where we were yesterday, at the end of yesterday. And again, all that stochastic approximation idea that I told you about, where you have a deterministic algorithm and you have a stochastic version where you're adding mean zero noise, and then you mix those two in these proportions related to alpha, right? That was another fundamental idea we talked about. So in stochastic approximation, you get this sort of box-like thing. And if you had the model, you would be sure that every iteration, your error would shrink by a multiplicative factor of gamma. But instead, of course, since you have mean zero noise added, you will not be exact. You will be some sort of ball around the expected value. But because you are doing this alpha-based shrinking, you get the right result in the limit. So here's a theorem for Q-learning. And again, this is a stochastic approximation-based thing like we talked about last time. If every state action pair is visited infinitely often and the step sizes, alphas, have the stochastic approximation properties, don't shrink them too fast. That is, the sum of alphas should be infinite, but don't shrink them too slow. Sum of alpha squared should be finite. All of that. Sorry, the other way around. Don't shrink them too slow, so sum of alphas is infinite, and all that, right? So we talked about this. Any questions about this before? Now I'm going to begin the material for today. Any questions about any of the things we talked about yesterday? Okay, good. All right, so let's keep going. I think I was almost at a point where I was saying, look, one thing we didn't talk about is how does Q-learning address the exploration exploitation problem, right? All I'm requiring is that every action be visited infinitely often. So in fact, you could take uniformly random actions and Q-learning will converge to the optimal Q value function. But of course, taking uniformly random actions for a long, long time is not a good way to behave. So how do we address the exploration exploitation problem? There are sort of two foundational techniques that other things have built upon. The first one is the epsilon greedy one. You've already seen that in the Bandit problem. Another pretty common technique in Q-learning is to use what's called Boltzmann exploration. The problem with epsilon greedy is that it's insensitive to the value functions, right? You take the optimal action with probability epsilon, probably 1 minus epsilon, and with epsilon you take every other action equally likely. So even if the second best action is just a little worse than the optimal action, you're not going to try that more. So you want an exploration scheme that's sensitive to the values. So that if there's a bunch of actions that have very high values and a bunch of actions that have very low values, you may want to explore the ones that have high values more than you want to explore the ones with low value. And that gets accomplished by this simple idea of Boltzmann distribution, where the probability of taking action A in state S sub t is given by this exponential form, e to the q sub t, the q value of that action divided by a temperature, tau, divided by a normalization term that just makes it a probability distribution. So if you hold the temperature fixed, you will do a fixed type of exploration, but sensitive to values. And of course, as you decrease temperature over time, again, not too fast, not too slow, you will get enough fast enough. You'll ensure that the conditions required for convergence are met. Okay, one other aspect of Q-learning that's important to point out is it's what's called an off-policy algorithm. So Q-learning, you behave however you want, as long as you're exploring enough, will converge to the value function of the optimal policy. That is, it's converging to the utility function or value function of a way of behaving that's different from how you are behaving. right? You could be doing purely random exploration and still converge to the optimal value function. It's called an off-policy algorithm because you're evaluating a different way of behaving than you are behaving, right? And that's a good thing and a bad thing. It turns out that it's a good thing because ideally what you want to be able to do is, because in the real world, you can only behave one way. But you want to be able to evaluate all different kinds of ways of behaving, even though you're behaving in one particular way. So off-policy is good. On the other hand, off-policy has convergence-related issues. So there's a standard algorithm that I want to just tell you about. It's called SARSA, which is an on-policy algorithm. So here, unlike Q-learning, it's very similar to a Q-learning update, but you don't do a max. So SARSA for SARSA. So Q-learning stopped at SARS. This is SARSA. So in other words, you take whatever action you take in the next state and use that action's value to update. So Q-learning had a max overall B, and an action was B here, right? Let's switch back to show you. Q-learning had, had a max overall B. You consider all possible actions in the next state into the best value. While for SARSA, you just take whatever action you took in the next state and then use that to get the value of the next state. So it's on policy. You're evaluating the way you're behaving. So now how do you guarantee that you converge to the optimal policy? Can anybody think of a way to do that? So if I'm evaluating the way I'm behaving, but I still want to converge to the optimal way of behaving, how might I do that? Try out lots of actions? Sure, you have to explore. But if I behave uniformly randomly, so unlike Q-learning, if you behave uniformly randomly, this will not converge to the value function of the optimal policy. What would it converge to instead? Just making you think, just so you don't fall asleep. I know it's the end of 2 weeks, so you must be tired. If you behave uniformly randomly, what will this converge to?
Presumably the value function for behaving uniformly randomly.
The value function for behaving uniformly randomly, right? Because it's an on-policy algorithm. So you can't behave, so unlike Q-learning, which is off-policy, you can behave however you want, as long as you explore enough, you'll converge to the optimal value function. Here, it's on-policy, so you'll converge to whatever it is, however it is that you're behaving. So but you want to explore, because if you don't explore, so here's what you can't do, right? Suppose you always pick the action that's greedy with respect to the current value function. You won't converge, because you're not exploring enough. You can get stuck. So you have to explore. So what do I do? The idea is we've been talking about them, right? So what do I do to make sure it converges? I have to explore, but not too much and not too little. So anybody?
The explore proportional to the reward. Like randomly pick between which.
Build an epsilon greedy. So I just explore epsilon greedily, right? With probability 1 minus epsilon, I take the greedy action. But when I take the greedy action, then this update is exactly the Q-learning update, right? Because it is the max overall B of AT plus 1 will be the max overall B, or all actions B. So when I take the greedy action, I do exactly the Q-learning update. When I do a non-greedy action, I'll do a different update than Q-learning would have done. So I explore by doing epsilon greedy, but then I shrink epsilon over time in order to get convergence. If I don't shrink epsilon over time, unlike Q-learning, this will not converge to Q star, because it will converge to the epsilon greedy behavior's value function. So and so here are two obvious ways to do it. You can do it in the epsilon greedy way, or you can do it in the Boltzmann way. So if you do 1 over t-like things, then you get the right amount of exploration, or you basically do log of n of t, log because it's an exponential here for the temperature. And either way, you can prove that, in fact, you do just enough exploration. And I'm not going to spend time on it, but you can also do the eligibility trace version of this algorithm. I did it for TD lambda. It's exactly the same idea, In fact, SARSA is very much like TD lambda, right? Very much like TD, because you are evaluating the way you're behaving, except you're keeping state action values rather than state values. So it's very much like TD. And you can do a TD, the eligibility trace version of it. And eligibility traces, again, let you do bias variance trade-off, just the way we talked about it for the temporal difference case. And so you compute the temporal difference error, which is exactly this quantity, and you maintain eligibility for every state action pair in this instance, as opposed to just states, and then you update every state action pair in proportion to its eligibility. So it's very much the TD algorithm, except it's exactly the TD algorithm, except you're doing state action pairs rather than states. Okay? And again, you get the same sort of bias variance trade-off. The larger the lambda, the more you are Monte Carlo, which means the more variance and less bias. The smaller the lambda, the more you are doing short-term updates, and the greater the bias and the lower the variance. And so somewhere between tends to work best. Okay. Any questions about this so far? All right. So now I want to finish off this section with a particular algorithm called delayed Q-learning. And basically, this is where we're going to do the optimism under uncertainty idea for exploration exploitation, right? We've done the epsilon greedy idea for exploration exploitation. By the way, can we do this phased thing? We could do this phased thing, I imagine. How would we, in Bandits, we talked about 3 different ideas, right, for exploration exploitation. Sort of the epsilon greedy idea, which we've been carrying through for MDPs. We're going to do, we talked about the optimism and uncertainty, which was the UCB1 algorithm for Bandits, and we're going to talk about the counterpart to that in the MDP setting with the slide that I have on the board. But there was an intermediate idea that we didn't talk about, that we talked about for Bandits, which was this phased exploration idea, which is we try every arm a certain number of times. We know how much we have to try every arm to get a certain amount of accuracy with whatever probability we want, and then pick the one that looks the best. Can we make up an algorithm for MDPs that looks the same? Anybody want to try? How would we do a phased algorithm, where we do a phased amount of exploration and then behave greedily? You look like you want to say something.
Couldn't you just take a completely random action every single time for a certain amount of time, and then once you've filled in enough state action pairs, then you just say, go greedy?
Yeah, that should work, right? Except for what? What's the issue? What's the challenge here? So here's the idea, right? The idea is you just say, you know what, I'm going to explore uniformly randomly, let's say, in the limit, pure exploration, uniformly randomly for n time steps. And then I'm going to switch to behaving greedily. And you might think, well, if n is big enough, then I'm going to be nearly at the optimal value function, and so it should be okay. What are the challenges? We talked about some of this for the discounted setting and the undiscounted setting in the early part of this material. So here's one challenge, right? Maybe you don't visit some state action pair. On the other hand, if you behave uniformly randomly, you're going to visit all state action pairs. If you're not, that means it's very hard to get to that state, and then maybe you don't care as much about that state. So I'm not going to finish this analysis, but I suspect that there is a way to do this sort of analysis where you can say, if I behave uniformly randomly exploratory for a while, then I know that I will be this accurate with this much probability. So I bet a phased analysis can be done. And in fact, what I'm about to do is very much like that, except with a little bit more twist, which is the idea of optimism and uncertainty. So, okay, so far the epsilon greedy analyses have been asymptotic, right? You converge in the limit, and I want a finite, a pack style result. So let me work my way towards a pack style result. So here's the idea: you initialize value functions optimistically, means larger than the true value function. So if you have a maximum reward of 1, then you can set say in the discounted setting, you can set the initial value function to 1 or 1 minus gamma, and that will be surely be optimistic. Here's how that works, right? Suppose, what's the maximum this sequence can be? Right, because this is a discounted sum of rewards. The maximum this can be is, if the maximal reward is R max, let's say without loss of generality, it's 1, then the maximum this can be, this is just geometric series, right? Or 1 minus gamma. So if you initialize value functions this way, you will have an optimistic initial value function. By the way, I didn't talk about this, right? But it's without loss of generality, you can assume rewards are bounded, right? At least an expectation. Because you can always add delta to the reward function and not change the value function for not change the partial order of policies, right? So let me say this again. You have an MDP. It has some whatever reward function it has. You add a constant to every state action pair's reward. You don't change the partial order of policies, right? The optimal policy is still an optimal policy. A bad policy will still remain bad, right? You shifted everything by a constant, so that doesn't change. So you can always get rewards into a particular range. Okay, so you initialize Q-value functions optimistically, and the trick is you maintain with high probability optimistic value functions. Okay, and then you choose actions greedily. So that's the idea, right? Just like from Bandits, optimistic value functions act always greedily. As long as the optimism shrinks over time, you will get convergence to the optimal behavior. So how do we do that here? It's a really straightforward idea. Here's what you do. You don't do an update at every time step. See, Q-learning in SARSA would update the value of every state at every time step. Sorry, of the state you actually encounter at that time step. Here you don't. What you do is you come up with a number m. We'll talk about what the intuition for the number m is. And you keep track of the last m times you visited that state action pair. You keep track of the last m times you visit that state action pair, but you don't make the update. Instead, you just keep track of the immediate reward you saw plus the discounted best value of next state. So V is max over all B of Q, right? The value of a state is the best value over all actions in that state. Okay, so you just keep track of all of these. And then when you've seen M, you make an update. But you don't just make an update with the average of the one-step discounted value, look-ahead value. You also add an epsilon 1. Okay, so here's the intuition behind this. If M is infinite, what can I say? If M is infinite, then I am doing something very specific. What am I doing? If M is infinite, then I'm doing exactly the Q value iteration backup, right? That is, if M was infinite, then I would have done the following backup. If M was truly infinite, then I would have done the following backup, right? I would have done the backup of R S comma A plus gamma sum over S prime T S A S prime V, whatever value S prime, right? I would have done exactly the backup I would have done with Q value iteration, as if I had a model. We talked about this yesterday as well, right? If you can do multiple backups at the same state, then that's like basically doing the model-based backup. So if M is large, I'm doing approximately the right backup. So I can ask, how big should M be so that this empirical M-step average is within epsilon 1 of what that would have done, or within epsilon 1 by 2. And then if I add an epsilon 1 to it, I'm very high likelihood maintaining optimism. Oh, that requires one more concept, right? If I start with initial value functions that are optimistic and do the exact Q value iteration update, then I will stay optimistic. If I were to do this update and start with an optimistic initial value function, then I will stay optimistic, right? Because I'm feeding in something optimistic on the right-hand side, so my left-hand side will also be optimistic. So I started optimistically. I didn't do the exact Q value iteration backup, which if I had done, I would have remained optimistic. But I did something very close to it by picking M large enough and by adding this epsilon 1 to make sure that I am staying optimistic with high enough probability. Remember, I'm getting a packed style result, so I'm getting a result with some 1 minus delta probability. And that's it. I'm going to stay optimistic. And as I do more and more updates, the Q values are going to get closer and closer to Q star. This epsilon 1 is going to prevent me from behaving completely optimally, but it's going to be nearly optimal. So I can get near optimal performance with probability 1 minus delta. So I'm not giving you a formal proof. I'm just sharing the intuition to you. The intuition is, so remember we talked about this intuition for bandits. If I have optimistic value functions, and if I ignore an action, then I should have ignored it. Right? This is the key idea. If I have optimistic value functions and I behave greedily, and as a result I'm ignoring some action, I should be ignoring it. So I'm maintaining optimistic value functions. And if I don't try an action because I'm behaving greedily, that's good. In fact, I want that to happen. It'll converge faster. You have your hand up.
Can you define optimism?
Sorry, I thought I did, but maybe I didn't. Optimism simply means I have a larger than the optimal value function. So I start with an initial guess of the value function that's larger than the actual optimal value function. So optimism is, I'm thinking every state action pair is better than it really is. So as long as I'm thinking everything is better than it really is and behaving greedily, then if I'm ignoring something, as long as the degree of optimism shrinks over time, right? If I'm arbitrarily optimistic and stay optimistic, well, then I could be doing arbitrarily bad things. But if the degree of optimism shrinks over time, then I'm going to not run into the problem that I'm not exploring enough. Yes?
And does that optimism, is that overall, or is that for state action?
Every state action pair needs to be optimistic.
But it has its own variable optimism.
It can have its own variable optimism as long as every one of them is shrinking to 0. Or shrinking to epsilon 1 in this instance. Why is it shrinking, by the way? Because I am doing these updates. I'm updating, every time I update a state action value, I am updating its value. Almost with what I would have done with a model-based Q value iteration update. Because if M is large enough, I'm doing almost the same update. You had your hand up.
This applies, I guess, to the optimal case, the optimistic case or the regular case. But in the times you're behaving greedily, except for the epsilon exploration.
No, I'm not doing any exploration here.
When you are behaving greedily, are you always choosing the maximum?
Yes.
Or do you ever do proportional to?
No. Greedy. This is the beauty of this optimism idea, right? I'm going to stay optimistic, but I have a technique that shrinks the optimism down towards 0. And if I can behave purely greedily and still ensure that I'm not under-exploring. It's a really key idea.
Wouldn't that mean that the suboptimal cases need to be optimistic enough to once in a while have a higher valuation than what you?
No, that's the key thing, right? Suppose let's take a suboptimal action. Suppose its true Q value is 10.3. And I set its value 10.35. So it's optimistic. Initialize its value. And I initialize every other state action pair to much larger values, 55. I'll never take this action, the suboptimal action. But that's okay. It's suboptimal. So you have to get this idea really carefully, right? Which is, look, here, imagine a particular state. Here are some choices of actions, and here are their true values. The height is the value. I start with optimistic initial value functions. So I start with, let's say I get this one just right, these two just right. So I'm never going to take these actions. I'm only going to ever take these two actions. And as the estimates get better, they'll shrink. The height will shrink, right? Always staying optimistic. So I'll never end up exploring these actions, but that's okay. Now, I could have started with an optimistic initial value function where this one was much higher. Then I would have taken this action a lot, even though it's suboptimal. But if I take this action a lot, its value will shrink. And at some point, it'll shrink below this. I'll start ignoring it. Right? That's the beauty of this idea of maintaining optimism. And as long as you maintain optimistic behavior, optimistic estimates, and it has a natural thing. You think this is a really good action. You're going to try it. And if it isn't good, you're going to shrink its value. If you think this is a really bad action, even though you have an optimistic guess, well, then it is a really bad action. You don't want to take it. Now, the difficulty is, of course, you don't know how to set a value function that's optimistic. So what you end up doing is you end up setting up everybody to the same value. So you don't get the benefit that I'm just talking about of being able to ignore really bad actions because you had a good guess of their value. But if you did, that would be better. Yes?
So how do you know that you're setting an optimistic, let's say it's uniform optimism, how do you know that you're above the actual value?
Because as I said earlier, right, if the Rmax, the maximal value of any state action pair is Rmax divided by 1 minus gamma. Because even if you get the maximal reward at every time step, which is unlikely, but even if you get the maximum reward every time step, then the best value will be Rmax plus gamma Rmax plus gamma squared Rmax plus gamma cubed Rmax. That's just a geometric series with gamma as the common ratio. Is that what it's called? So it's, right, you know this geometric series formula, right? If you have A0 plus A0R plus A0R squared plus A0R cubed, so this is a geometric series where R is less than 1, this sums to 1 minus R. So I just use that trick. I teach discrete math in college, so this is one of the discrete math tricks. Okay, so everybody happy about this one? All right, that was it for my idea for MDPs. Now I'm going to switch to 3 different topics that I'm going to cover about roughly 1 hour each. But let me summarize this part. So I think I've explained to you now most people in reinforcement learning will not agree with the statement that I'm about to make, which is that I've basically explained to you the key ideas of reinforcement learning. In some sense, probably the strongest, biggest ideas in reinforcement learning. One of it was the temporal difference idea. It's probably the heart of reinforcement learning. But what does temporal difference address? Exploration, exploitation, or a delayed reward? Which one of the two does it address, or maybe both? What does the TD idea address? What problem is it addressing? Exploration, exploitation? Or is it addressing the temporal credit assignment problem? Which, I talked about 3 big problems in reinforcement learning, right? The delayed reward, the exploration, exploitation, and generalization. So I'm claiming that TD is sort of the foundational idea in reinforcement learning. Which of these issues does it address? Maybe all of them. Anybody? Come on, you can answer this question. Yes? Sorry? Yes, it is a learning algorithm, but which of these 3 issues is it addressing? Generalization, exploration, exploitation, or temporal credit assignment, equivalently delayed reward? which one of these issues is the TD idea addressing? What is the TD idea? You update the value now based on a one-step delayed value. Which of the three is it addressing? Come on. Delayed reward. Yes. Temporal credit assignment. It's not addressing exploration exploitation. Right? Okay. So TD was the idea, and TD lambda more generally, eligibility traces more generally, is the idea for addressing delayed reward within reinforcement learning. And it meshes very well with the dynamic programming Monte Carlo approaches from the operations research literature. That was one key idea. Another key idea I addressed here was the idea of sampling of Monte Carlo as a means around the curse of dimensionality. So there the idea was Monte Carlo methods. So I talked about, you want to evaluate a policy, you do multiple random walks with that policy, average, and you can get a good estimate of the value of a state in samples completely independent of the size of state space. And then we talked about a similar idea for sparse sampling, which was finding a good action in every state, which also used Monte Carlo ideas to find the best action in a single state in number of samples or computation that's independent of the size of the state space. Now, unfortunately, sparse sampling needs a model. Delayed Q-learning, on the other hand, does not need a model, and it has similar sort of properties. Okay, so those are two key ideas. Eligibility traces was another key idea in reinforcement learning, which is about bias variance trade-off. I talked about that. And then this idea of optimism under uncertainty as a means of addressing exploration exploitation. To me, these are the foundational ideas within reinforcement learning on which lots of fun stuff has been built. The thing I didn't address is generalization, of course. And there, I think, for the most part, as I said to you, we've been borrowing ideas from supervised learning, which is where much of the action on generalization has happened. Okay. Did I have more slides on this? Oh, yes, I do have more slides on this. I totally forgot about the last bit of this thing. All right, that's good. I'll finish up by noon, and then we'll have 3 one-hour sections. So now I'm on the last part of this small MDPs idea, which is I'm going to talk about model-based learning. Recall that I've been talking about model-free learning. So TD and Q-learning don't build models. Even delayed Q-learning doesn't build a model, even though it does an update that looks like an update that you would do if you had a model. So what's the most obvious way to do model-based learning? So model-based learning is different from planning, right? Planning, you're given a model to begin with. You can do offline computation, find a good policy, and then behave. Model-based learning is learning. You're not given a model to begin with. You can interact with the world and learn a model and use planning methods with the learned model in order to behave. So this is a very short section. Let me get at that. So the simplest idea in a small MDP setting would be to learn the transition probabilities and the reward functions. That is, to use the empirical estimate of the probability of a transition from state S to S prime on action A. So this N is just the number of times you've seen this transition or a number of times you've taken action A in state S. So this is the empirical estimate. Actually, it turns out it's the maximum likelihood estimate under the usual sort of Dirichlet sort of assumptions of the state action next state probability. And similarly, the expected reward is just the average, the empirical average of the reward you've seen in a state action pair. So here is the first simple idea of model-based learning, right? Learn a model. Can you behave greedily with respect to the current model? So you've behaved so far. You build a model from all the experience you've gained so far. You can compute the optimal policy with respect to the learned model. That's called the certainty equivalent policy. That is, you assume that the model that you have is equivalent to certainty. So certainty equivalent policy. Now, could you just behave according to that policy and be sure that you will converge? No. Again, exploration exploitation hasn't been addressed. So, but you could do epsilon greedy, and that would be fine. So if I do epsilon greedy with shrinking epsilon exploration, this simple idea will converge to the optimal model, and the optimal policy with respect to the optimal model is optimal, therefore you converge to the optimal policy as well. Now you could do uniformly random exploration, that's fine too. Your model will converge, and the optimal policy with respect to the model will converge even though you're behaving very badly. But you could do epsilon greedy with shrinking epsilon if you want to ensure model converges, and your behavior converges as well. Okay, so this is the simplest idea. Let me give you a one step up clever idea which addresses the exploration exploitation problem more completely. So to motivate the E cubed idea, I'm going to point out a particular problem with the previous approach, which is behave randomly, build a model, and then behave greedily, then behave optimally with respect to that model, with some exploration. Yes.
Just for understanding, well, you try to model it space and policy, right?
Sorry?
Here we try to model it, try to model the space, our states with space or policy, right?
Let me, where I had a white thing in my hand. Give me a second. Okay, it's gone. What we are modeling is the transition probability in the reward function. A model of an MDP is the transition probability in the reward function, from which we compute good ways of behaving, value functions, and policies. So we are modeling the transition probabilities in the reward function, right? That's what's up there. Transition probabilities and reward function. Did that answer your question? Yeah. Okay, so that's what we are modeling. That's what we are building a model of from the transitions you experience. Okay, so what's the problem with this approach? The biggest problem with this approach is that basically you can have problems in which behaving uniformly randomly or randomly is going to take a very long time, basically exponential time, in the size of the state space to learn a good model. What's an example? A combination lock is an example. So combination lock is a problem in which you have two actions, the solid action and the dashed action. And the dashed action brings you back to the start state. So if you do any sort of exploration, random exploration, you'll have very little likelihood to get to the end. Right? So you start here, you take what looks the good action, the solid action. At some point, you'll do an exploration action, you write back. Right? So the number of time steps needed in order to visit this state is exponential in the number of states. So you will not learn a good model very efficiently. So just uniform exploration, even epsilon greedy, right? Whatever epsilon is going to take a very long time to learn a model in this sort of world. So in fact, there was a result that says learning in MDPs is exponential in the size of state space and actions. The general problem of learning in MDPs was known to be exponential in the size of state space and actions. And basically, let me give you the next idea, which I'm going to talk about. It's called E cubed. And we showed a result that basically goes like this. We showed that, in fact, you can learn, it's the Pack-style result, that in basically polynomial time, in the size of state, space, and action, as well as something else, which we call the mixing time. Polynomial in all of these three quantities, you can learn near optimal policies for discounted and undiscounted settings. I'm going to focus on the undiscounted setting in this conversation. So we went from having a result that says exponential in states and actions to a result that said the only way it's exponential is if the mixing time is exponential in size of state space and actions. What's the mixing time? A mixing time of a policy is, or an epsilon mixing time of a policy, is the number of time steps you have to run that policy so that your distribution over states experienced under that policy is epsilon close to the stationary distribution, the limiting distribution of that policy. So in this combination lock example, the random policy has exponential mixing time, exponential size of state space, because it takes you exponential time to get to the end. Okay, so now what I'm going to show you is the idea behind the E-cubed result, which shows you how to ensure that, so get a pack style result basically for this sort of thing. So here's the idea. Let me show you a picture. Here's a result, formal result. An algorithm E-cubed takes inputs epsilon and delta, and then for any value function and mixing time, holding in the MDP. Now what do I mean by that? V star and T star holds in the MDP if there is a policy in the MDP that mixes in time T star and gives you utility V star. Then in total number of actions and computation time that's polynomial in 1 over epsilon, 1 over delta, T star, and number of states, you get to within epsilon of V star with probability 1 minus delta. So how does this work? Here's the idea. It's really quite straightforward. Again, we'll have a number m, which is the number of times you have to visit a state action pair before you've seen it enough, before you say that that state action pair is known. So at any given point of time, so I'll tell you how to think about that number m in a minute. But at any given point of time, some state action pairs shown in solid are known, and some state action pairs are not known, shown in dashed. So you know some state action pairs and some other state action pairs you don't know. The way you do E-cubed is you construct a special MDP by taking all the state action pairs you don't know and collapsing them into a single state. So everything you don't know is this purple state. And then here's how you do exploration exploitation. You say, look, if I can find a way of behaving, so you say the unknown is really bad. You give very low reward, minus R max, to the unknown state and compute the optimal way of behaving in this MDP. If that's good, if that gives you near V star return, then you know you can take that policy and actually get that much return. Because the good way of behaving in this MDP, where you have made the purple state very bad, will avoid that state. And therefore, will keep you within the known part of the state space. So if there is a way to basically solving the optimal policy by making the purple state very bad, tells you if exploitation can give you V star return, V star utility. And if it can, great, do it. And if it cannot, then what do? You do the next. You do this trick. You set the value of the purple state as very good, R max. And then the optimal policy will try to take you to the purple state as quickly as possible. Or in other words, take you to a state action pair that you have not visited often enough. So that's the exploration exploitation idea. You have a threshold M, which tells you when you get to know a state action pair. What do I mean by that? I mean I've seen that state action pair so many times that I know its transition properties pretty well. And this is, again, sort of regular Monte Carlo Hoeffding sort of bound, okay, which we talked about yesterday. And so if you've seen that state action pair that many times, you call it a known state action pair. If you haven't seen it, you call it unknown state action pair. You collapse all the unknown state action pairs. And if you ask, can I exploit by making that unknown purple state really bad? And if you can, then you exploit. If you cannot, then you set that purple state to be very good. and then find the optimal policy, which will take you to the purple state as quickly as possible, which means it'll get you to revisit a new state action pair that you don't know enough about quickly. And so you get fast exploration. This idea making sense? I'm exploring and exploiting by labeling the unknown things as either very good, which will lead me to explore, but it'll take me to places I haven't been to, or labeling it very bad, which will tell me how much I can expect to exploit by avoiding things that I don't know. So that's the idea. If I want to exploit, I set things that I don't know as very bad. If I want to explore, I set things that I don't know as very good and find the optimal way of behaving and behave according to one or the other. Yes?
So how good do you need to be to ignore the unknown stuff? Will you be epsilon optimal or
Yeah. So part of the trick is to figure out how, what should exploitation give you so that you don't have to explore. And there, the algorithm requires a particular kind of search that basically the idea is, the trick is to keep increasing that threshold. And as you increase, you will ensure this packed style result. But actually, it turns out there's a much simpler way to do all this. So I want to talk about that in a minute. And that's this idea. So here is now, E-cubed started this sort of optimism under uncertainty, right? Optimism under uncertainty for exploration, because you set the purple state as very good, you treat it as optimistic, as things you don't know can be very good. There's a part of gold in things you don't know. And so you go there. So that's the optimism and uncertainty idea. But there's a much more simple algorithm that accomplishes very similar effects. It's called Rmax. Here's the idea. You initialize the value function optimistically. You have the same M, which is the number of times you have to visit a state action pair. If you visit a state action pair M times, you update its value. Otherwise, you don't. But you update it using the estimated model, T hat and R hat. So it's a really straightforward idea. I am bouncing around the world. I'm going to behave greedily. Every time, I'm keeping a counter for every state action pair. Every time that state action pair's counter is more than M, I update its value using my latest model. Now, since M is large enough, my model is going to be nearly accurate, which means that this update is going to maintain optimism. Exactly what we did in Q-learning, in delayed Q-learning, right? This is very much like delayed Q-learning, except you're not doing the empirical average, you're doing the estimated model. And you only update states once you've visited state action pair, when you've visited a state action pair at least M times. And this maintains optimism, and as the model gets more accurate, as you visit state action pairs, your model gets accurate everywhere, and it works. So this is a much simpler way of doing the same thing as E-cubed did. You just keep around, you start with an optimistic value function. You keep track of how often you visit every state action pair. Every time you visited a state action pair M times, M is large enough. M is a function of epsilon and delta, right? The smaller epsilon is, the larger M will be. The smaller delta is, the larger M will be, because the less error you can afford in the model. So M grows with epsilon, 1 over epsilon, 1 over delta, and that's to be expected. And then you do the update. Your T hat and R hat, your estimated models, are close to accurate. You started optimistically, the high probability remain optimistic. So very similar to delayed Q-learning, except you're building a model. Okay, and you can prove the same pack style result for for this algorithm as one does for E cubed and for delayed Q learning. Yes?
So I didn't quite, could you go back to the theorem?
Yeah. The theorem looks pretty, here it is.
Yeah, so is it that if there exists some policy that has good reward in fast mixing time, you will effectively end up doing something that's like that?
So here's another way to think about it. The longer I run this algorithm, the larger the set of policies it'll compete well with. So every policy has, so if you run the algorithm for this much time, there are some subset of policies that mix within this much time. If you increase time, then more policies will mix within that much time. So as you increase time, you're competing with longer and longer mixing time policies. Now, of course, the optimal policy is what you care about, and that will have its mixing time, which could be much shorter than some other policy's mixing time. So you'll do really well quickly if the optimal policy has or a good policy has small mixing time. Any other questions? We are almost at noon. So I think you've seen a pretty elaborate tutorial on small MDPs. No generalization, right? Planning, learning, exploration, exploitation. So I've basically shown you how exploration, exploitation, and temporal credit assignment are addressed in the small MDP setting where you don't have to worry about generalization. By the way, how would we address generalization? We'll stop after this. We try to think of an answer to this question. How would we address the generalization issue? So we talked about chess the other day. You can't do any of these techniques on chess, right? Too many boards. How would you address generalization? There is an obvious way to address generalization. What's the obvious way to address generalization? Sorry?
Some form of regularization?
Yeah, but I want a simpler answer, sort of the first step. What's the first step? So all this while, by the way, I've been keeping lookup tables, right? I've been keeping counts for every state action pair. I've been keeping numbers for every state action pair. I can't do that anymore. So what do I do instead? I could do linear regression. I could do decision trees. I could do anything you've learned about regression. Right? Any technique for regression can be employed where I have some features now of a state action pair, and I'm mapping those feature values to real numbers for Q values or V values. And if I want to learn a policy, if I want to explicitly learn a policy, then that's a classifier, right? In this state, do this action, this state, do this action. Yes?
Are there different forms of classifiers that tend to lend themselves, or in practice that tend to seem to work better, or just depending on the problem?
Yeah. Unfortunately, in reinforcement learning, the guidance for what function approximators to use isn't super strong. Usually what happens is, if you're a Gaussian process guy, you'll do Gaussian processing. If you're a linear regression person, you'll do linear regression. Personally, if you ask me, I'm a fan of linear methods. So I think linear methods tend to do reasonably well. So you build a very large feature representation, do kernels if you need to, and then do linear things on top. I'm a fan of those. But other people disagree and do other things. And if you want a machine human understandable kind of thing, then you want to do, decision trees or something like that. But where you want the output to be human understandable. But in general, any function approximation method that you can use can be used. There are challenges, though, and I'll talk very briefly about those challenges when we come back. All right, enjoy your lunch.